last week we talked about the suffix and the prefix, right? Yeah, the DP problem. So today we're actually doing another DP problem. Yeah. Okay. So okay, just like a quick review. The suffix problem, and there's the prefix. Okay, so what is the difference between these two?
Suffix means you're going from the end.
Yeah.
And then prefix means you're going from the beginning.
Okay. Right. So suffix problem, like so one of the suffix problem we did before was the blackjack problem, and so the reason was that the cards were dealt from the top, and each time one card. Okay, so imagine this is a deck of cards, like if you pay on the table, and each time basically we deal a card from the top. This is all of the cards. So each time you deal one card, and so the cards that's left on the deck is basically the suffix part, which is like from like all the other parts that remains is the suffix. So yeah, that's basically why blackjack problem is the suffix problem. Okay, and the text justification problem is also a suffix problem, right? So we talked about this before, and this one's actually kind of tricky and not as obvious as the blackjack problem. The reason is because so when you're doing the text, right? So it's kind of intuitive to think about like if you have a list of words. Sorry, let me just read it here. So if you have a list of words and you try to put this list of words and split it in the right way to put in the Word document and have it look as nice as possible. So intuitively, you want to think of this as like as an IJ problem, right? Instead of a suffix or a prefix problem, because you always think that maybe you need to figure out where the text starts and where the text ends, and that seems like an IJ problem, but this is actually a suffix problem because you can always assume that the text will start on the next line at exactly the beginning of the next line, so you don't have to guess where the so you don't have to guess where the text starts because the text always starts with the first text that's remaining. So that's kind of the tricky part why this problem is not suffix or prefix. Sorry, why this problem is not an IJ problem but rather a suffix problem. Yeah. So so this week we're doing like the third type of problem, which is the IJ problem. Okay, so remember that. Okay, so the way it's defined to be a suffix, to be a prefix, and the IJ problem is in the way that's like of the structure of the DP, like the DP subproblems. Okay, so the first case that like the subproblem is can be expressed using the like basically a suffix, this notation, and the other way is also the same, that the prefix subproblem can be expressed in this notation. So IJ problem it's just the same, that you can express it using like basically and j, two variables. Okay, so yeah, we're gonna do one example of we're gonna do one example of the so we're gonna do one example of the IJ problem this week, and then we want to code it out. So depending on when we get that done, this session can be like shorter than before. Okay. All right. I'm just it's kind of messy, but okay, I'll just write this down. Oh, let me just say briefly what the like the problem we're doing today. So it's called the longest palindrome subsequence. So it's called longest palindrome subsequence, and so basically, this is one of those very famous palindrome problems you can see. So I know that on LeetCode there are plenty of problems about palindrome, and a very typical example is that, so say you have a, let me think about one example. Yeah, so say you have a like one word, like any word. Like this is also a good example because easy version of the palindrome problem would be asking you like, so what part of this substring of this string would be considered a palindrome? First of all, do you know what a palindrome means?
Yeah, it's the same going forwards and backwards.
Right, exactly. So a palindrome would be just a word that's I don't know, AKA. Okay, this is not a word, I guess, but this is we consider a palindrome because it's forward and backward, it looks exactly the same. Okay, so, but the point is that, okay, so an easy version of the longest palindrome problem is that it's asking you what part of the substring is considered to be a palindrome. And that will be easy because basically, like you know that a substring can be continuous, right? A substring, okay, so this part can be considered a substring. And a suffix, a prefix are also substring, right? Because they basically just continuous part of the string, starting with the end and the beginning. Okay, so that's the easy part. And in this case, but it's not actually substring, right? It's asking you the subsequence. So if you want to solve the substring problem, right, it's actually quite simple because all you need to do is just to use 2 pointers, right? I don't know if you're familiar with this idea of 2 pointers, but here I'm saying pointer, but it's actually not like literally the pointer in C++. It's actually just you can imagine this as 2 indices, just ij, right? So you can just, what I mean by ij is that these are basically the indices for 2 loops. And so basically I just will go over all of the possible indices of this whole string, and j will also go over the whole string. And I basically indicate where the string will start, and j will indicate where the string will end. So you basically permutate all of the possibilities and for the substring, right? Because say for example, I is equal to 0 and j is equal to like within the for loop. At any moment in the for loop when I is equal to 0 and j is equal to 4, this will basically give you this substring, right? Okay, right. So this will be like an example that why this can be used. Why this is called 2-pointer techniques, because it's literally using 2-pointer to indicate where the current substring is. Okay. So any question here about the longest palindrome substring, not the subsequence? Okay. Okay. So now we're going to the subsequence part. Okay, so the problem is a little bit challenging for the subsequence because right now the substring has to be continuous, but the subsequence doesn't have to be. And note that what do you think is the longest subsequence for this specific word?
Is it just E? Does it have to be in order or no?
Okay, so yeah, so sorry, I forgot to mention that. So it has to be in order. Basically, if you pick this two, right? If you pick E and this E, right? That was a good guess, but okay, that's actually the answer. So if you pick E and E, right? So let's say if you pick E and this F, right? This F, and then okay, you can put E here and F here, but okay, you can't put this K here. You can't really do that because this K is actually before the F. But you can put this K here because it's actually in order. But let me think. Yeah, so you can put this way, but you have to use this K. So subsequence also has to be in order. That's the only constraint, right? But other than that, you can use any part of the substring, and just put it in order and construct a new string. Yeah. So the okay. So the right guess is that the longest subsequence for this string is actually just this E F E. Right? So it could be anything within this this range. Right? Could be E F E, could be E K E, and F E, R E, anything. Just this string doesn't matter. Could be any string. That's what matters is that it has to appear within this range in order for it to be ordered. Yeah. Okay. So any question here?
No.
Okay. So all right. So I guess we'll go to the how to solve this D. Okay. So okay. Yeah, I don't think this problem ever appeared on LeetCode. I know that the 2-pointer substring problem appeared on LeetCode, but this one I don't think so. It's a bit more challenging for the LeetCode problem. I'm not sure. Okay, so what do you think would be the idea for the brute force? Like, how do we utilize brute force to solve this problem? Or like, I actually before that, do you have any like questions over what this problem is about? Or
No.
okay, all right. So yeah, do you have any idea like how the DP problem can be like deployed for this case?
How to what?
Like how to use TP techniques to solve this problem?
I don't know.
I mean, or brute force. Like, how do you think of using brute force to solve this problem?
Brute force, first do length 1, and then you iterate through it once.
Yeah.
And then you do length 2, and then you just choose like any 2, and then length 3, and then you iterate and choose.
That makes sense.
Yeah.
Okay, so you think that, okay, so basically, so let's say we're, if you use the brute force way, you're basically saying that we pick any of the, like, okay, so basically there are all possible, like, what would be the possibility here? So, okay, so we know that the first, like, okay, so the result string we're gonna construct is gonna be of length something, right? Of length, I don't know, x. And so we want to decompose this into several parts, or just 2 parts, doesn't matter. So the first part can be the length of x1, the second part the length of x2, right? And then you want to like basically exhaustively find all of the possible strings for the x1 and x2, right? I mean, also could be more parts, right? It doesn't have to be 2 parts, right? Because this is uncontinuous, so it can be more parts. So it could be x1, x2, and all the way onto x, right? And then each of these parts is the part of the resulting string, and all of them in order. Basically, you exhaustively find all of them, and then you construct one string, which is the x, and then check if that's a palindrome or not, and until you eventually find the longest. Is that what he's saying?
Yeah.
Okay. Yeah, that makes sense. But okay, so what would be the runtime like complexity for this? Like in this case, what do you think?
Wait, sorry, what was the question?
Like, what would be the like complexity or runtime complexity of like this algorithm?
The length of the string to the end power?
Actually, okay, so the length of the string is in, right? To the to something.
Do we know what x is, or do we have to iterate through possible x's?
I mean, okay, so we will here. I think we have to permit like all of the possible cases for x1, x2, all the way to x8, and then like try them all of them. Okay, never mind. It's a tough question. Yeah, but okay, let me think about the whole complexity here. Okay, so basically this is like a choice question, right? So there are many different choices, and for the first one, like for the x1, right, we can pick anywhere of the length of x, like 1 all the way to like x n over 1 over 2 all the way to n over n. Right. So only for x1, that's all the possible cases. Like you can pick anywhere of a string of length 1 of all of the like the whole string, and all the way to all of the whole string. So that's all the possible cases. So so it's actually quite a lot. So yeah, this is definitely not the optimal solution for like solving this problem. Yes. Okay. Now let's think about what would be the DP problem, like DP approach to solve this problem. Okay. Do you have any like guess of how to solve this problem in DP? All right. So do you want to just go over like the whole process?
Yeah.
All right. Okay. Yeah, I mean this problem is quite challenging, so I'll probably just go over like how to solve the problem, and then let's try to code it out. That's basically the whole point of this one. So. All right, let's try to. I'll just go over like how to solve this problem using DP now. I'll make it quick so that we have time to code. Okay, so the what will be the subproblem for this one? Let me think about that. So as I said, this problem is of type ij. So basically, okay, so the reason why it's called ij is because the subproblem is defined using like two indices. And you can imagine why is that the case, because for any word, right? Sorry, I keep using this example. So for any word, right? So the palindrome can be starting at any index, right? And ends at any index. So those two are all like free to choose. That's why it has two indices. So in this case, okay, so I'm just gonna write the subproblem in this case. So it kind of encourages you to define it in the way that you want to use two indices. One denoting that where the string starts, the other one where the string ends, right? So then you want to think about, okay, so that's how, okay, so what does this, so we need to define that how this is the DP table, right? It's using two indices, but what does this thing denote, right? So what does DPID denote? What do you think?
Wouldn't it be like DPIJ?
Yeah.
So starting at index I and ending at index j.
Exactly. So yeah, I know. But what does this value denote? Equal to?
For this problem?
No, I'm like, okay, so sorry. Maybe that was a bad question. I'm saying that, okay, so what DPIJ is equal to, let's say it's equal to some number, right? If it is equal to number A, what does this whole statement denote? Like, what does it mean?
It means like how optimized it is, right? Or like how good or bad it is.
Yeah, sort of, but okay. So, I mean, this might be a weird way to ask this question, but each time you denote this kind of a DP notation, you want to ask yourself, like, what am I? Okay, so you sort of want to ask that, what does this thing denote? So, okay, I'll just self-explain what it means. Okay, so this basically means that for the this DP question for this string starting at index I ending with index j. So the longest palindrome is of length A. Okay, so for example, okay, so given that this E starts as index 1, right? And this last E starts as index 10. Okay, so starting at index 1, end with, let's use an inclusive notation here. So starting with index 1 and end with index 10, right? The last E is at 10. So this will be E, F, E, E. So this will be 5, right? This makes sense. Does it make sense?
Yeah.
Yeah, and if, let's say if it's from 0 to 2, what would it be?
It would be 1. I mean 2. Sorry.
Oh yeah, 2, exactly. So it would be E, so that would be 2. Right, so this is the DP part. And we basically want to denote this DP notation table then. Saying that, so starting at index I and with index j, what is the longest, what is the length of the longest palindrome? Yeah, that's the thing we're trying to build out using recursive or like the bottom-up approach. Okay. So now the next question is what would be the guess? Like, okay, so this is the subproblem. Right. So the second thing is that we want to have a guess. And we want to get something that's related to the eventual solution. So any guess, like what do you think we should be guessing here?
Guessing the start and end index.
Yeah, exactly. So we want to guess that where the I and J's index starts. Basically, that would be like a permutation of like the first I could be all of the from 0 to 1, right? And the second one could be for each of them, the second one could be of 10. Yeah. So it's about n squared, right? This will be n squared like runtime complexity. Okay. But okay, that's part of the guess. The first guess is that we want to know where the I and J should start. Right. But the next question, the second part we want to guess is what will be the length of the IJ. Does that make sense? Sorry, not the length of the edge, but what will be the length of the string that contains our optimal palindrome? Yeah. So for example, okay, so what will be the length of the string that contains this palindrome? It would just be from 1 all the way to 10, right? This string contains our palindrome. And, I mean the longest palindrome. And also, so yeah, okay, so I'm just thinking how to say this more clearly. Okay, so I'm trying to think. So yeah, so basically, we want to guess what will be the length of the string. That contains the longest palindrome. Okay, yeah. So the reason we're asking this is because okay, remember that what we did for the which question was that? Oh yeah, okay. Remember what we did for the Bellman-4 algorithm? So remember that when we're trying to find the yeah, no, this is kind of like very far away from your memory, but let's try to think about what's like the similarity. Why we're guessing that? Okay, remember what we said for the graph problem. So we want to start with the single source node and we end with the V node, and we're trying to find what would be the shortest path in this case. So the thing we were guessing back then was that, so what would be the incoming edges into V, right? The last incoming edges into V that gives us the shortest path, right? So, okay, so, but the trick we were using that gives us, do you remember what the trick we were using gave us the, like the, basically, a cyclic DP graph?
The trick that gave us the DP graph?
No, I mean like the, remember that, so, okay, so basically back then we were solving this problem, right? And we had originally a diagram or a direct acyclic graph that basically we were computing and each of the subproblems. But then we encountered this case that when we're computing this subproblem, and we need the knowledge for the original problem. And this forms basically a loop, right? And we say that this would cause an infinite loop because you don't have knowledge of this problem and it's basically keep going, right? So we used one trick to basically resolve that problem is that we used basically this notation. So originally we have this DP table, which is beta SB. So this originally we had this notation. Then after we introduced one trick, right? We basically used this and this. Let's just say that. So yeah, we basically used this trick that we're using n edges at most from S to B. So after using this trick, so we basically we're n from 1 to all the way to all the number of nodes minus 1. Right. So at most you can use n minus 1 edges, and at least you need to use 1 edge. So after using this notation, we basically exploded this like cyclic graph into one that's not cyclic but multiple. Remember these crazy graphs. So originally this was a cyclic graph, but after introducing this graph, like using this notation, right, we basically exploded the whole graph into a one that's not cycle, that doesn't contain any cycle, where our DP doesn't have this sort of like infinite loop problem. Yeah, so this was a trick that back then we were using. So actually we're using exactly the same trick here, that we are guessing the length of the string that contains the longest element, where the length just could be from 1 all the way to the whole string. Right? So this basically shares similarity with that. So you're gonna see that a lot of DP problems, you want to have this sort of I don't know how to phrase it properly, but I guess just so if you introduce one more variable, but that's gonna like make DP doesn't have like that's gonna make the DP acyclic. Yeah. So you don't want to contain any So I mentioned that this like the DP problem is more like a graph problem, right? So you can represent any DP problem in the way that a directly acyclic graph does, but you don't want to contain any cycle. So whenever you use this sort of trick, you introduce one more variable, and the graph gets exploded, so it doesn't contain any cycle. But the two graphs are equivalent, just the second one doesn't contain cycle. That's the beauty of it. So, all right. So, okay, I'm just gonna. So this is the same we're gonna guess, right? So the length of the string that's contains longest boundary. Okay. So, all right. The next thing is we're going to see how to relate each of the subproblems. Okay, so the all right, I'm just going to draw the graph first. Then, by the way, sorry, I'm going so quick like today. Just the point is that we want to code it down. So I'm just going over the whole like DP process.
Yeah.
Okay. So the acyclic graph looks like this. Okay, so this is how the whole DP basically how the whole DP brings together. So each of the node, remember what the node denotes?
It's like the indexes that you're checking.
Yeah, exactly. So the node basically denotes the so like two parts, right? Each of these is the subproblem. And remember that the way we define the subproblem is that we use two indices. Right? So this is the DP table, and this defines the subproblem. So this is basically saying that, so starting with the zero indexes ends with zero indexes. So it's in inclusive notation here. So this will be the longest palindrome that's, the length of the longest palindrome that's within the range of from 0 to 0. And this is 1 to 1, 2 to 2, 3 to 3. And then we can find, like this is how the DP computation flows. So after computing this, each of this is the base case, right? And we basically done computing each of this. And then we bring down, like use some transition function, right? Isn't after the right, we haven't covered what the transition function would be, but suppose that we done the right transition function, we're able to bring the each of the DP base case results down to one like further, like one other results. That's, I mean, we haven't computed yet, but so this is basically saying that we're gonna use two results. One is the longest palindrome from index 0 to 0, basically the first index. This one is the second index. And we're going to bring them two together into one further subproblem. That's so this is basically saying that what will be the length of the longest palindrome from index 0 to index 1. Does it make sense?
Yeah.
And this part is just saying what's the 1, 2, 2, 2, 3. And do you know why we like doing it in this order?
It's because in order to know the one below it, you have to know the one above it.
Yeah, exactly. Okay, so that's exactly right. But so the reason is because I said that we're gonna do it in the order that's from basically from one, like the order we're guessing is from 0 to n, right? Right. So here, if you see that the first DP zeros base case is where the case where it's less than equal to 1. And second one is less than equal to 2. And that's 3 and that's 4. So this is the length of the string is just 4. Sorry, the length of the string is 4. So basically it's just each character, which itself is a palindrome, right? One character itself, let's say it's an apple. This is the word that I'm trying to compute the longest palindrome. So the base case will be just that 0 will be just A, right? This will be a palindrome itself. So let's try to run over like what will be the computation here. So for this word, right, apple, how do we compute the longest palindrome? So the first step is that we want to compute each of the base case. So the base case is that so the first character A itself is 0, 0, right? So that will be 1. And this part will also be 1, 1, 1. Right? So each of those will be 1. Because each of the characters itself is a palindrome. And after done computing that, we want to use some transition function to bring us down to the second layer. Okay, so the first one in the second layer is saying that what is the length of the palindrome for this, like, longest length of the, the length of the longest palindrome for the, from the index 0 to the index 1. And second one is saying from index 1 to index 2. Third one is 2, 3, so on. Okay, so let's now go to the transition function, which is the last part, right? So this is the subproblem, transition function, and the base case, the somewhat guessing, the subproblem, and the transition function. So we're almost there, so just on the transition function now. Okay, so what will be the transition function? So transition function literally just is to notify those errors. Sorry, not errors, right? So, okay, so I'm just gonna write it down. But we're gonna code it later. So the transition function will be. So remember, there are two forms of transition functions. At least, as far as I know, there are two forms. One is that it's a mass function, right? The case where we had in the Fibonacci number. This is a mass formula. And the second one is a logical flow, like it's a logical condition. And in this case, we're doing the logical condition here. So the transition function will be the logical condition that. Okay, so that's literally all we have now. So that graph basically represents the whole thing. This graph is all like unique. Like if you're able to come up with the graph, because this graph really just encompasses all the subproblems, the senior guessing and the transition function. So yeah, all we need to figure out is what the transition function is. Very long. Okay, that's it. Oh, can you see it?
Yeah, I can see it.
Alright, so transition function is basically saying that, okay, so this is the logical flow. This is the condition. before the condition. So the first condition is that j minus I is equal to 1. Second one is that si is equal to sj. The last one is ss is not equal to sj. Okay, so I said this is a condition, so it does have a order in which if you implement like the if you do like say if you write code, right? If you do the logical loop, it has order, right? The first order will so the first condition will be executed first. It will be checked first, and after that, if it doesn't match, the second will go, right? So this like logical loop also has order. So when you look at the DP, so when you implement this will be the first if condition, and this will be the second, and last will be the third. So this is basically saying that I'll briefly say what each of these conditions mean. So the first condition is that if j minus s is equal to 1. So this is the case where so if you have a word, right? Okay, you have a word. This is basically saying that the first index is I, second index is j. So when these two indexes, so basically you have so when you have so when you have a j right next to I, so in this case, so I is the first a, and j is equal to the second character. So when you have I and j right next to each other, this is the first condition. So this is saying that what is it saying is that when you have so basically it's just like two characters, right? When you have two characters, you just check if these two characters are the same or not. This is the base case, because this is the base case. So it's basically saying that if you have two characters, you're checking that if the two characters are the same. If it is the same, then you have the length of the longest palindrome equal to 2. Otherwise, it's 1, because if it is the same, then just combine them together. It's just in this case, so in this case, P and P will be this case. So P and P would just give you 2 this case. But A and P would just be 1, because A and P is not a palindrome. But you check this by checking that SI is equal to SJ. So this is saying that the string SI index as string at J's index. Alright, this is the first condition. The second condition is saying that so if the S index is equal to J's index, so say that let me see if this is a good example. Yeah, okay. Let me just fix it. Okay, so say that if you have you're trying to compute this part. So I'm saying that this part. So you try to compute the longest palindrome of basically any parts that's after G and before K, right? So the longest palindrome is just the ESE, right? Or EFE. So, but when you're trying to compute this part, this DP case is saying that you want to look over the part that's I plus 1, J minus 1. So you want to look over this part, like the part that's sorry, it's a little bit messy. Can you see it? Or
Yeah, I can see it.
okay, so this is saying that you want to look over the parts that's inner, basically the inner parts, after this E and before this E, and you want to look over what will be the longest palindrome for this part. And this case will be just we know that the longest palindrome will be EFE within this inner part. Because because you check that the S character is equal to J's character, the E character is equal to this E character, and the inner part longest palindrome is EFE. So you just append these two characters to this inner palindrome. Because if the inner part is the palindrome itself, and the outer two characters are the same, you can just append the outer two characters onto the inner palindrome, and they form basically one bigger palindrome. Does that make sense? Or?
Yes.
Okay. So this is basically the second type of condition. So I think this transition function is actually quite hard, like this part. And normally, if you come up with the the sub problem is already pretty hard. Like you need to think of what type of DB problem this is. And there could be 3 possibilities as far as I know. And after that's defined, you have to think of what you're guessing in order to have the right answer. That's the guessing part. And last part is the transition function. I mean, the fact is that if you come up with the first 2, right, you have a narrow idea what the transition function will be like, but it still takes you a while to exhaustively find all of the cases. And in this case, it's kind of hard to find all the exhaustive cases.
Yeah.
Because there are actually 3 different types of transition functions, and you have to put them in the right order. Because you can't execute this one before this one. Do you have any idea why that?
Because in order for you to execute the second one, you have to know if the first one's true.
Yeah, that's true. But also like, okay, so if this one is put after this one, right? So you check this one first. So I plus 1, j minus 1. Let's say if I is equal to 1, j is equal to 2. So if you put this all like this transition function after this one, so you check this one first, then this one is actually trying to check that dp I plus 1 and dp minus 1. I plus 1 is 2, minus 1 is 1. So actually you're trying to check the indexes. So remember that this is like a word that starts with index 2, ends with index 1. It doesn't make any sense. So you have to make sure that they go over like the base case first. That's exactly what you said. But you have to go over the base case first before moving on to the like this case. That's why like the order of the condition also matters. So you have to put the transition function in the right order as well. Yeah, but essentially what this is saying is that, okay, so you have 2 characters being the same. You just append these 2 characters onto the inner longest palindrome, like, and then you have the longest palindrome, like at the current state. This is the second transition function. The last one is that, okay, so if you have the last one is basically saying that, okay, so it's saying that the case where so let's draw this. Never mind. I draw it. Okay, so the last one is saying that if you have so if you have this word, I'm trying to find the longest palindrome of starting with, okay, you find starting with this e, the same e, but ends with this k, right? So this e and this k. So what would be the longest palindrome within this bond?
It would be EE, what are the middle terms EE?
What's that? Sorry?
Wouldn't it be EE, what are the middle terms EE?
Exactly. Yeah, that's right. But okay, that's right. The third function is saying that, so you want to do the max, right? So max is basically saying that one possible case is that so you are to compute this this longest palindrome. You have to find like the previous 2 you already computed, right? Mm-hmm. The one is that EE, the one that we just talked about, right? This part. This part is already computed, right? Which is the E and E. And the other part is from this part to the K part. From this E to this K. Because you see, here is I j minus 1. Here is I plus 1 j. So the other one is I plus 1. So it's from the second E instead of the first E. The first value is starting from the first E, but the second one is starting from the second E. And ends with K, but the first one ends with E. So the first one, the longest palindrome is E at E. The second one is actually, let me think what the second one would be. It's actually something like E at E. Yeah, it's actually E at E. So yeah, so you want to take the maximum of them, which is this case. So essentially what the last one is saying that if you can't form a new palindrome that's longer, you just want to preserve the longest one you had previously. Yeah, this is literally what the last statement is actually saying. In this case, if you can't form a new palindrome because you have a k and k doesn't form any like longer palindrome, so you just want to preserve the the longest palindrome you had before, which is E and E, rather than using like rather than taking the shorter one. Yeah. So does it make sense or?
Yeah, it makes sense.
Okay. So the second case is saying that if you can form a longer polynomial, just add t. You append them onto it. If you can't form the longest polynomial, you just preserve the previous one. You have fun. That's the longest. And the first case is saying that base case. The first case is basically the base case where there's only 2 characters. Right? So if on the graph, we see clearly, okay, so this transition function, so the one that I'm currently marking, corresponds to the first logical condition. Because here is actually j minus I is equal to 1. Right, so those like the upper transition functions correspond to the first one. And everything else, just those transition functions, match to either of those two, depending on which logical condition you actually executed. Right. So any question?
No.
Okay. So yeah, I guess I will have 2 options, but I'm gonna stop recording now.